Okay. Many of you have noticed that Stats 131 has now been listed by the registrar, so that's exciting. It'll be offered next quarter in the spring. Monday, Wednesday, Friday, 2 to 2:50 p.m. will be the lecture time. We have 75 seats, okay, and so for this first time, I think demand will exceed our capacity, so we're gonna run a lottery to get in, and so you should have received an email. At least I emailed this class, and then we're gonna email the other stats seniors as well. So basically, if you're a senior who's graduating in the spring or summer, okay, and a statistics major, you are eligible to sign up, and then we'll run a lottery. Okay, we want to give priority to our stats majors and our seniors who are graduating, because they won't have an opportunity to take the class, right? And then if you're anybody who is younger or who's not graduating this spring or summer, then the class will be offered in the future, and so you'll have a chance to take it then. Okay. All right. Let's take a look here. I've also posted homework 3, and I'm trying this thing out with and without hints, and we'll see how that goes. I always view the homeworks as a little bit of a problem-solving puzzle type thing, and so if there's too many hints, it takes the fun out of the solving, right? So anyway, I guess fun is a subjective term, but I encourage you guys to do your best on your own, and then of course if you need some hints, the hints file is available. And who knows, maybe even after the hints, maybe my hints aren't good enough, but I'm hoping they help. Anyway, there's also a lot of text that I'm hoping you read through. And then for today, I wrote a whole bunch of text, and I'll post this up as well, because we'll talk more Bayesian stuff. Okay. All right. So to cover kind of our Bayesian things, we said, we left off and we said the beta distribution is the conjugate prior to the binomial distribution. The beta has alpha and beta shape parameters, and this is what we'll do. Okay. So let's okay. So we have kind of again more Bayesian ideas. All right, and we said the posterior distribution. Okay, this is a probability distribution of our parameter based on the data, right? Given the data, right? So probability distribution for our parameter. Based on observed data. This is going to be probability of, in our case, theta given our data x, or, well, okay, the textbook uses y, all right? And this is going to be the likelihood, the probability of getting our data for a given parameter times the prior distribution on that parameter divided by the probability of our data, okay? And then we said this thing is complex. This is just a constant with respect to theta. So this reduces to the probability of theta given y is proportional to probability of y given theta times the probability of theta. Okay, and so for our carnival coin flip scenario, probability of y given theta This is the binomial. This is a binomial distribution, okay? And then probability of theta will be a beta distribution. Technically, probability of theta could be any distribution, but the beta distribution is the conjugate prior to the binomial, which means it has nice mathematical properties. So I think on Friday we went through just like if theta, our prior distribution said there were only two possible coins in the world. Here we're going to say it's the beta distribution, but so it could be any distribution, but using the conjugate prior, gives us nice properties. Okay, and so if we say, all right, well, what does the beta distribution or the binomial distribution look like? Okay, so actually, if let me just write this as probability of y given our parameter r. This part is equal to n choose y sub n, r raised to the y sub n times 1 minus r raised to the n minus y sub n. Okay, this is the binomial, so that should be familiar. And then over here, the beta distribution, the probability of our r, given shape parameters alpha and beta, you get this crazy thing, gamma alpha plus beta divided by gamma alpha times gamma beta. Okay, I think on Wikipedia they have, they just call this thing the reciprocal of this thing beta or something. But anyway. And this is times r raised to the alpha minus 1 and 1 minus r raised to the beta minus 1. So that's what we have. Okay, and then so when we combine these, and I say the probability of r given our data y is going to be equal to the probability of y sub n given r times probability of r. This becomes n choose y sub n times r raised to the y sub n times 1 minus r raised to the n minus y sub n times the crazy beta gamma nonsense. Don't worry about the gamma distribution. The gamma function is just, the gamma function is like the factorial function, except made continuous. So, like, but it's like shifted over by 1. So like 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial is 120. What if we like made a smooth curve that connected all of these things? Then you'd get basically the gamma function, but it's just like shifted over. The gamma function just acts really crazy weird when you go into negative numbers, right? Because when you do like negative factorials, then it starts like flipping signs, and so ignore the negative side of the gamma function. Well, not ignore it, but anyway. Okay. So anyway, this, if we're like, okay, you know what? We will say, all right, this is just some constant, and this thing is just some constant. We'll just combine these together, and we will just say this is going to be equal to we'll just say, well, not even equal, I should say, is proportional to, all we do is we just add these things up and we say r is going to be raised to the y sub n plus alpha minus 1, and then times 1 minus r raised to the n minus y sub n plus beta minus 1. Okay. And that's what we have. And then the textbook says let delta equal y sub n minus or plus alpha, and let little gamma, so little delta and little gamma equal n minus y sub n plus beta, and then this reduces to, this is supposed to be proportional to r to the delta minus 1 times 1 minus r to the gamma minus 1. Okay. And then if this is the case, then this resembles the beta distribution with shape parameters little delta and little gamma. Okay, and then so if we want the total thing for little gamma, then you have, you know, the whatever this thing is, right? You have some constant times r to the delta minus 1 and 1 minus r to the beta minus 1. Okay, or not beta minus 1, little gamma minus 1, sorry. We're just continuing using different letters. So AB, I guess we want ABDC, but okay. And then if we think about, so if we think about the kind of, not the exact meaning of this, but you know, if we think about the shape parameters alpha and beta in the beta distribution, okay, alpha can be thought of as, you know, how many times have you seen the coin land heads? And then beta can be thought of as how many times have you seen the coin land tails? Okay, and then later on, so then in our posterior, we get a beta. So this is our prior, right? We get a beta distribution with shape parameters delta and gamma. Okay, and delta we said is going to be alpha plus y sub n, and gamma is equal to beta plus n minus y sub n. I guess I don't need these parentheses here. Right. So we have that in our notes, right? So if we think about what this means is basically, what is y sub n? Y sub n is how many times the coin landed heads in our new set of data, right? And then n minus y sub n is equal to how many times it landed tails in our data. So the updated shape parameters is effectively just how many times total have we seen the coin land heads if we combine our prior number of coin flips with our current data coin flips. So if our prior distribution was, we're going to come in thinking that this coin is centered around 0.5 using shape parameters 5 and 5, it's basically saying, so far, my prior feelings about this coin is that I've seen it land heads 5 times and I've seen it land tails 5 times. And then we flip the coin 10 times and it lands heads 6 times and tails 4 times. So my updated distribution will have alpha equal to 5 plus 6, 11, and beta, or I guess gamma, equal to 5 plus 4, 9. And so I'll have a new distribution with shape parameters 11 and 9, which will be centered not at 0.5, but just shifted a little bit over to the right. So we're just basically updating our beliefs, and this is why the beta distribution is the conjugate prior, in that it has this nice property in that it kind of makes this intuitive sense in that if we think of the alpha and the beta parameters as how many times we've seen the coin land heads and how many times we've seen the coin land tails prior to our current collection of data, and then we incorporate what we saw in the data, then our stuff gets updated accordingly in a way that I think makes logical sense. Okay. All right. So I've created this document called Bayesian Ideas, and you can download it and load it up and render it. And it's like a wall of text. But I guess I'll I'll read through some of it, and I'll kind of point out how we can illustrate some of these ideas here, okay? And you can go in your own time mess around with this. There's a little video put on by the people at Stata on covering Bayesian ideas, and so the first part, the first 5.5 minutes is, I think, recommended viewing, and then the rest, when they start covering how to use Stata, you can skip it. Okay, so again, the big idea is frequency statistics and maximum likelihood estimation. We just try to say our parameter theta or r, whatever it is just a single value, and we use that for our future estimates. And here we're going to say we're going to express our beliefs about this theta distribution parameter as a probability distribution. Okay? And we said the posterior distribution looks like this, and we covered all of this, and we said because this thing is just a constant, we can just have it in this form where it's proportional to. Okay? And so we'll take a look, and this is we're going to do the beta binomial relationship, at least for today, and then I guess on Wednesday we'll look at other things. Okay. Okay, and so first of all, I created a function called win_probability based on the description of the coin game in the book, which was you flip the coin 10 times, and how often does it, if it lands heads 6 times or less, then you win, right? And so if we're playing with a perfectly fair coin, we have about 83% chance of winning, okay? On the other hand, if we're playing with a weighted coin, such that it is, has a 90% chance of landing heads, then we only have about a 1% chance of winning the game. Okay. And so we will consider 2 scenarios. One scenario is we flip the coin 10 times and it lands heads 6 times. And then we'll look at another scenario, which we'll call scenario 2, where we flip the coin 100 times and it lands heads 70 times. And from here, we're going to create likelihood functions for these two scenarios of data, okay? And so to do this, I'm just going to start by creating a vector R that starts at 0 and ends at 1, because this covers the entire span of all the possibilities of my coin parameter R, right? Because you're not going to have a coin that lands heads more than 100% of the time or less than 0% of the time. So we just go from 0 to 1, and I'm going to just take a step, by make a vector of basically 1,000 values, 1,001 values. And then I will calculate the likelihood of my data. So I'm just going to say, what's the probability d binom of 6, 10 for all the different values of R? I get 1,001 values for the likelihood. And then I say, do the same thing with 70, 100. So what's the probability of getting 70 heads out of 100 flips for all the different probabilities R, okay? And then I get a vector called likelihood 2. Okay, I just throw this into a data frame, and I use tidyr to gather the columns into a single thing, and I create this likelihood plot. Okay, so the likelihood plot shows if I flip the coin 10 times and I see 6 heads, then that data outcome is most likely when the probability of heads is 0.6. Okay, it is still possible if the probability of heads is 0.5 and at around 0.4, it's still possible. And even when the probability of getting heads is only 1/4, it is still possible. It's not very likely, but it is still possible to flip the coin 10 times and get 6 heads. Okay. On the other hand, when I have 100 flips and 70 heads, that is most likely. The maximum likelihood happens when R is 0.7, okay? But then if I go down to R is 0.5, if I'm using a fair coin, this plot basically says the likelihood of that thing happening, of getting 100 flips and 70 heads, is close to 0, okay? It says it's very, 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 very unlikely for you to flip the coin 100 times and get 70 heads if you're dealing with a fair coin, or anything that's has a chance of heads even less than that. One thing we'll notice is that this curve is taller than this curve, okay? And that's because likelihoods are not probability functions. Probability functions must integrate to 1, likelihood functions do not, which makes sense because the scenario of getting 6 heads out of 10, overall, that likelihood is much more likely than the scenario of getting 70 heads out of 100. Okay, even if we consider all the different possible outcomes of R, getting exactly 70 heads out of 100 is just less likely of a scenario, even if you had a biased coin, than it is to get 6 heads out of 10. Okay, and so our likelihood functions do not integrate to 1. Later on, when I illustrate these, because the likelihood functions will be so small sometimes, I'm going to normalize them and make them integrate to 1. Okay, I'm going to just multiply them by a constant to make them integrate to 1. But effectively, they don't have to. Okay, so the prior distribution, we said we're going to use a beta distribution, and we're going to look at 3 different prior scenarios. Okay. And one we will say is a flat prior. This is called the uninformative prior, which is this, okay? This means every possible outcome between 0 and 1 is equally likely. So this is the flat prior. So these are probability distributions. These all integrate to 1, okay? Because they represent the probability distribution on R. So the uninformative prior in blue basically says all values between 0 and 1 are equally likely. A coin could land heads 100% of the time. It can land heads 0% of the time. Here, in green, we are going to assume that the coin is fair, okay? Meaning that the coin will land heads 50 the coin lands heads with probability close to 50%, maybe a little bit higher, maybe a little bit lower. We're open to the possibility. And then lastly, in red, we have the biased scenario where we are assuming that the coin is biased towards landing heads more often than tails. Okay. How we express the prior distribution could be different. So here I used beta shape parameters 50 and 50 for the fair scenario. Okay. I could have used 5,000 and 5,000. What 5,000 and 5,000 would have done would have made my prior very, very, very pointy at 0.5, okay? And basically very unlikely, so it'd be like the only possible values allowed would be somewhere between 0.49 and 0.51, okay? And in fact, to the extreme, we could just say, I could come in with the prior belief that every single coin on Earth is fair, that that no such thing, that an unfair coin does not exist. There's no such thing, and so every single coin on Earth is 0.5. And maybe that's true. I have no idea. But and basically, if I came in with that prior belief, I would have 0 everywhere and just a spike at 0.5, I guess infinity tall. Okay, so that it integrates to 1, and that basically means that. Because the posterior distribution is the product of our prior with our likelihood, okay, way back up here, or is proportional to it, our likelihood times our prior, that no amount of data could convince me otherwise. Because if I have 0, if I say everything else has probability 0 and only 0.5 is the only thing that's possible, then no amount of data will convince me otherwise. Even if you show me a coin that lands heads, 100 times out of 100, I'm going to look at that and say, this does not fit in with my prior belief about the world of coins, and therefore, I will I can multiply the likelihood of that thing, which is very small, but whatever, it doesn't work out. Okay, so the prior belief doesn't will not be adjusted. So you don't want to have too skinny of a prior. I mean, you can, but then it just means you're really basing your beliefs on the prior. Okay. All right, and then the marginal distribution is the probability of y. Okay, just our data, which goes into our denominator here. But this can be expressed as the integral across all possible values of r for the product of probability of y given r times the probability of r. So this thing, when we multiply this out, this is the probability of y and r. And so you have the joint distribution of y and r here, and then if you integrate across all possibilities of r, you basically get rid of the r, and you're just reduced with the probability of y sub n. Okay. And so again, the nice thing about this is that this is going to be just a constant with respect to r, and we can get an approximation of this by performing Riemann sums. Okay, so Riemann sum would be basically it's just grid estimation, right? So instead of doing the actual integral, we're just going to calculate the function and then basically add those up times the width of our interval, right? So basically, if you wanted to integrate r dr, which is, or I should say x dx, which is x squared over 2, that integrates to 0.5, you could approximate that doing r times delta r, and in this case, we would have 1,000 values from 0 to 1 multiplied by 0.001, and if we do that, we get something very close to 0.5. It's a tiny bit off because we got 1,001 values rather than 1,000, but whatever. Okay. So we get 0.5. So here I'm going to basically we've already calculated our vector of likelihoods. Okay, there's 1,001 values here in this vector of likelihoods and 1,001 values here. And then I've got 3 vectors of priors, and those are all vectors of 1,001. And so I just do element-wise multiplication across these two things multiply it by the width between each estimated value in those vectors, and then I sum them up, okay? And so this will give me kind of the marginal values for all of these different things, which, you know, right now don't mean much, but what we can see is that, you know, what is the likelihood of getting these outcomes under different priors? They vary a little bit, okay? And we see that the likelihood of getting the second scenario where we flipped 100 coins and got 70 heads, those likelihoods, those marginals are much smaller in general because that data is much less likely to begin with, okay? And so the posterior is just the likelihood times the prior divided by the marginal value, okay? And so I have produced this just by simply doing this. I've got my vector of likelihoods, my vector of prior values, and I'm going to divide it by the constant in the marginal, okay? And I'm going to call this, so the likelihood of scenario 1 being 10 flips, 6 heads, multiplied by the prior, assuming it's a fair coin, divided by the marginal, is going to be the posterior of scenario 1 under the fair prior. I got posterior 1 under the uninformative prior, and I got the posterior of like scenario 1 under the biased prior. Okay, so I've got 6 different kind of posterior distributions. Let's just plot these out and take a look here. Okay, so here my likelihoods have been normalized so that they integrate to 1, and that's just so you can view them. Otherwise, the true likelihood function is much, much shorter and looks like it's just that somebody stepped on this and flattened it out, and you can't really appreciate what it looks like. Okay, so the prior, I don't know if you guys can see this. This is the blue line centered at 0.5. Okay, this prior assumes fairness, meaning my alpha and beta, I use shape parameters 50 and 50. So it's as if I had seen 50 heads so far and 50 tails so far. So right now my beliefs about the coin are that it lands heads with probability 0.5. In the data, we saw 10 heads, or 10 flips, and 6 of them were heads, okay? So the likelihood there is most likely at 0.6, but, you know, all of these other values are also possible, even though the likelihood associated with these are lower. The posterior is what happens if I combine my prior belief with the likelihood. I get a new distribution that's just shifted ever so slightly to the right because my data favors something that shifts over to the right. Okay, so that's what we see here. If we take a look at this one here, again, my prior belief assumes fairness at 0.5, 0.5, okay? At 0.5 with 50, alpha 50 and beta 50 for the beta distribution. Here, my data was 100 flips and 70 heads, so the likelihood function is right here, okay? Centered at 0.7, this is going to be the maximum likelihood estimate. When I incorporate, multiply the likelihood times the prior, I get the posterior, okay? So the blend between this and this gives me something in between. And so my prior beliefs had alpha 50 and beta 50. Basically, I'd seen 100 flips so far. Half of them were heads and half of them were tails. And then my new data set was another 100 flips where 70 were heads and 30 were tails, okay? So if I add those two together, it's as if I had seen 120 heads and 80 tails, okay? It's as if I'd seen 200 flips with 120 heads and 80 tails, and therefore my most likely scenario there is centered at 0.6, okay? And so here we have this, and when we kind of merge these two together, we get something centered around 0.6. So that's what we have there. Okay. If my data had something like 400 flips and whatever 280 heads, okay, then this likelihood would be centered at 0.7, but would be skinnier and pointier and more narrow, and then the posterior would also be a blend between this and this, but it would be a lot closer the posterior would probably be closer to like 0.67 or something, because now the likelihood carries a little bit more weight there. Does that kind of make sense? Do we see the relationship here between the prior, the likelihood, and how it's the posterior is kind of like a hybrid between the two? Okay. Here, the prior made no assumptions about the data. We said everything between 0 and 1 is possible, okay? And so my likelihood is just the likelihood function, centered with a peak at 0.6, okay? And if I plot the posterior is dependent entirely upon that likelihood, because the prior made no assumptions about our data beforehand, okay? And so because our prior made no assumptions about our data beforehand, then what we see in the data will determine all of our beliefs about R, okay? And so the posterior lines up exactly on top of the likelihood, okay? And I had to change the line thickness of the likelihood so that you could see it underneath it. Otherwise, it looked just like one line, and that the likelihood wasn't plotted. But it is. It's just the posterior goes exactly on top of it, because in this uninformative situation where we are making no assumptions about R, then the data will determine everything we believe about R. Okay? And we have the exact same thing happening here. Again, we make no assumptions about R. We have an uninformative prior, and so what happens in our likelihood determines everything we believe in the posterior, which is what we have here. Okay. Does that kind of make sense? Okay, and so, and again, because we observed more data, so over here we observed only 10 flips and 6 heads, there's quite a few possibilities for what R could be. Over here, because we saw 100 flips and 70 of them are heads, then we can still be pretty confident that R is not going to be 0.5 or 0.3, because our data would not be possible under these other values of R. Okay. All right. Over here, we've got the prior being biased. So here we are assuming, before we even look at the data, that it's biased towards heads. In fact, our largest value happens when the probability of heads is 1. We look at our likelihood, which is centered at 0.6, and thus our posterior is adjusted so that it kind of is a blend between the blue line and the red line to give us kind of our green line here. So this represents something as kind of a compromise between the blue and the red. Okay. Similarly, here's our prior, and my likelihood is this, the red line, which is quite pointy, and because this one just carries a lot more weight, yes, the posterior is a compromise between the blue and the red, except it puts a lot more weight towards the likelihood, and matches that up with that a lot more closely. Okay. All right. Is this okay? And we could draw like even more kind of combinations between the prior and the likelihood, and then we'll see that the posterior is kind of like a blend between these two things. You can go through and mess around with creating new vectors for the prior and the likelihood and the posterior. I'm hoping this code is not so difficult to translate or parse. I guess I can add more text. Okay, so once we have our posterior distribution, which is kind of this line in green that appears in each of these things, we can then go back and answer our original question, which is, what is the probability of winning the game? Okay, so at the very beginning, we said, what's the probability of winning the game, which is, what's the probability I get 6 heads out of 10 flips? Okay, And we said if the coin was had a property of 0.5, we would have this probability. If the coin had a probability of 0.9, we would have this probability, so on and so forth, okay? So here I can just graph what's the probability of winning the game, and we can see, you know, if the coin lands heads, you know, anything less than 0.4, you're almost guaranteed to win in that you will get certainly less than 6 heads out of 10, okay? But as when the PR is equal to 0.6, then your probability of winning is right around 1/2, okay? Which makes sense, okay? Because then it's like you don't know if you're going to get 6 heads or more, or 6 heads or less. And then when the probability of landing heads is something close to 1, then it's almost guaranteed that you're going to lose, okay? And so this represents kind of the curve for what's the probability of winning. And effectively, here I have basically 1001 values, so I've got another vector that's the same length as my posterior and everything like that. And so to do this, we're just going to do another kind of Riemann sum in that I take this vector of win probabilities. So it looks like it's a smooth function, but this is really just 1001 values spaced out between 0 and 1 that are just very close together that your eye merges them into a single line. Or actually, I tell R to connect it with a single line, or connect it with 1001 line segments. So it looks like a line, but this is just a grid approximation, right? If I only had 10, then there would only be 10 dots along here. But I've got, you know, 1001 grid approximation points, and I would do 1001 here, the winning probabilities multiplied by the posterior. So basically I say, you know, what is the probability that I would win if R was equal to 0? And it says, well, you would win for sure. That happens with probability 1. But then according to our posterior, what is the probability that R actually is 0? Well, the posterior says that has a probability of 0. So the product there is going to be 0, right? And then so we kind of have to look at, you know, the combination between our posterior. And so if we look at the first scenario, posterior, where we assumed 1 and fairness, okay, our posterior distribution on this graph goes from here to here, okay? And so basically we get values that aren't 0 starting around, I'm going to just say 0.4 and ending around 0.6-ish, okay? And so it's basically saying the values from 0.4 to 0.6, these are the most likely ones, okay? And so when we kind of multiply these things out and do the integral between the product of these two, then that probability is 0.8. So this would be my estimate of winning the game according to my posterior beliefs about R if my prior beliefs were that the coin was fair, right? So if I'm inclined to believe that the coin is fair, before observing any data, so when the coin was fair, I believed that the probability that I would win was 0.828, around 83%, okay? I go in still with those beliefs that the coin is fair, okay? However, I observed 10 observations such that 6 of them landed heads. So now my updated probability is just reduced ever so slightly, okay? Instead of 83%, it's now around 80% because now I'm incorporating the fact that I saw somebody play the game, they got 10 flips, and they only saw 6 heads, right? Okay. Actually, let me skip down to here. If I still went in with the belief that my coin was fair, with you know, centered at 0.5, it used to be that the probability that I would win was around 83%. I observe 100 coin flips, and 70 of them ended up heads. So now, if I incorporate what I observed there with my prior beliefs, I would say, okay, the coin probably lands heads a little bit more frequently than 0.5, and because of that, the probability that I think I'm going to win is going to be reduced to around 0.614, okay? And we can see how the different prior beliefs will affect the outcome here. So here, if I had no beliefs, the uninformative prior, and I observed just 10 flips and 6 heads, then this is not going to be not much different than having a point estimate of using 0.6, okay? And similarly, if I came in with an uninformative prior and I observed the 70 heads out of 100 flips, this estimate will be close, not exactly the same, but pretty close to saying using a point estimate of around 0.7, okay? But then everything else here, so here I'm coming in with the biased perspective, thinking that the coin is very unfair, and so so here, after viewing the outcomes, then the probability that I'm going to win is lower at around 0.39, and so on and so forth. And that's and so we can kind of use our probability distribution representing our beliefs after viewing the data to then answer our original question, which is what's the probability of winning? And the probability of winning is no longer based on a single point estimate, but rather on the entire distribution of all the possibilities for our parameter value there. Okay, yeah, this is a lot of text. You can read through it to just make sure you understand everything else, but I hope that makes sense, and we'll take a look at this in kind of some other applications on Wednesday.